All right, so the purpose of this video is to look at how you can represent functions with power series. So first of all, we have now learned how to write a handful of functions in series notation. So for example, we are able to write e to the x as this series, so we could write that as the sum of from n equals 0 to n equals infinity of x to the n over n factorial. So we know how to do that. We can write sine of x and cos of x. We know this geometric series. And while we haven't looked at arctan before, we could similarly expand arctan into series notation. And these are the following radius of convergences. So e to the x, sine, cosine, and 1 over 1 minus x. E to the x, sine x, cosine x will converge for all values of x. Our geometric series here has a radius of convergence of 1, so in this case the absolute value of x must be less than 1 for it to converge, and arctan of x is the same. Okay, so we can use these series to answer a lot of other questions. So for example, let's say that we wanted to find the convergence for this following function, f of x equals 1 over 1 plus x. What we notice is, well, this really is just, we could rewrite that as 1 over 1 minus x. And then we recognize, oh, this is following in the pattern of a geometric series where we have n equals 0 to infinity, a starting value of 1, and a multiplier of negative x. And so the question is, find the convergence. Well, we know that the convergence would be that negative x, absolute value, must be less than 1. So x, therefore, is between 1 and negative 1. And it has a radius of convergence of 1. So what we're starting to do is look for patterns in other functions that we can fit into our known functions. So in other words, we're trying to fit them into these known functions here. Okay, so now find a power series centered around x equals 1 for the following function. All right, well, let's think about what we know. If it's going to be centered around x equals 1, we know that we need to rewrite our following problem as f of x equals 5 over 3 minus. And if it's going to be centered around x equals 1, we need to do a shift. So we have x minus 1. Now it's centered around minus 1. Oh, sorry, centered around 1. And then plus 1. So we haven't changed a thing, only now we recognize that this allows us to express it as being centered around negative 1. Well, if we do a little bit of algebra, we get 5 over 2 minus x minus 1. A little bit more algebra. So divide everything by 2. We're going to get 5 over 2. So if we divide each of these terms by 2, we get 5 over 2, 1 minus x minus 1 over 2. Now this is falling into a geometric series. So we get that our a value is 5 halves, and our multiplier, r, is x minus 1 over 2. So what's the radius of convergence? Well, we know that our R value, x minus 1 over 2, must, absolute value, be less than 1. And therefore, if we were to expand this, we get that x minus 1, absolute value must be less than 2, and x must be between 3 and 1. Small little mistake here. This should be a negative right there. So that should be a negative 1. And we see that our radius of convergence equals 2. So again, what we're doing here is we're taking some function and we're manipulating it to look like something that we know. So we're either making it a geometric or e to the x, sine x, cos x, or tan x. All right. Let's think about this graph or representation. We've got a function e to the negative x squared, and we know that we know how to write e to the x, right? So e to the x is just, well, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. But now what we have is a composite function. So everywhere where there's an x, instead of putting in an x, we should be putting in negative x squared. So e to the negative x squared is going to equal 1 plus, well, instead of x, we're going to have negative x squared plus negative x squared over 2 factorial plus negative x squared cubed over 3 factorial plus plus, well, let's think about that nth term in a second. So if I rewrite this a little bit expanded, we have 1 minus x squared, and then for this, the minus is going to go away because it's being squared, so we're going to get plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. The next term, what we think is going to be, well, plus x to the 8th over 4 factorial. So how could we write this? Well, we could write that. Let me get rid of this. We could rewrite that whole thing as the sum from n equals 0 to infinity of negative 1 to the n, and that's what's going to cause the oscillation or the alternating of positive negative, times x to the 2n over n factorial. And that's the kind of slow substitution way of doing it. We could do that a lot quicker if we, once we become comfortable with this process. So let's think about how you could do that a lot quicker. So what you could jump to is, we know that e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. So then we could just directly substitute into my series notation. So e to the negative x squared is going to equal the sum from n equals 0 to infinity. Just plug this right into there of negative x squared to the n over n factorial. And then we can expand, or rather distribute the exponent. So this would equal the sum from n equals 0 to infinity of negative 1 to the n times x squared to the n, which is x to the 2n, all over n factorial. And we get the exact same thing. So when we have a composite function, we can just go right to the series notation and do the composite substitution. So let's do that right here. It says find a Taylor series that represents cos of x. Well, we know that cos of x we can rewrite as the sum from n equals 0 to infinity of -1 to the n times x to the 2n over 2n factorial. So therefore, cos of root x, we're just substituting this root x in for x. So that's going to equal the sum from n equals 0 to infinity of -1 to the n times root x to the 2n over 2n factorial. Well, we know that root x we could re-express. So we could re-express root x as just x to the 1/2, because that's the same thing. And then that makes it a lot more clear that cos of root x could be expressed as the sum from n equals 0 to infinity of -1 to the n times x to the n all over 2n factorial. And, where does this converge? Well, we know that, let's get this away. We know that cos of x converges for all x. Cos of x converges for all x. So cos of root x will converge for all x that's in the domain of root x. So it's going to converge as long as x is greater than or equal to 0. Because if it were less than 0, it would be outside of the domain of root x. So power series can be integrated or differentiated just as you would integrate or differentiate any sort of function. So you can obtain new series by differentiating or integrating, and your result will have the same radius of convergence as the original series. So when you integrate something, the radius of convergence stays the same. When you differentiate it, it stays the same. So let's look at an example of that. Let's suppose we wanted to find a power series representation for this following function and find its radius of convergence. Well, if you look at this, what is that? Well, we could rewrite that function. We know that the derivative of 1 over 1 minus x equals, well, if we think about taking the derivative of 1 minus x to the -1, it would be -1, 1 minus x to the -2, times the derivative of that inside, which is -1. So we would get back 1 over 1 minus x squared. So therefore, the derivative of 1 over 1 minus x is this. Well, we know that 1 over 1 minus x, we can write that as, well, a value of 1 and an x value, sorry, a multiplier of x. That's what 1 over 1 minus x is. But we want to find the derivative of that, because the derivative of this is, well, these two are equal. So the derivative of 1 times x to the n should equal 1 over 1 minus x squared. And I'm ignoring an important piece of this. We're talking about the sum from n equals 0 to infinity. So now let's just take the derivative. Well, the derivatives work exactly the same. N is just it's a number, it's a constant. So the derivative of this is going to equal the sum of, well, the n drops down, n times x to the n minus 1. Well, what is the counter going to be? So in other words, where's my initial index value going to be? Well, let's actually take a second to think about that. So if we were to kind of take it a little bit slower and say that the derivative of the sum of all this, well, that would be just the derivative of 1 plus x squared plus x cubed plus x to the 4th plus dot, 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 dot. The derivative of that is going to be, well, if we take the derivative, that's going to be 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 dot. So our first term needs to be 1. Well, how do we get our first term to be 1? This value here must be 1. And we go to infinity. And then let's just check to see if that works. So when n is 1, we have 1 times x to the 0, which is 1, plus, when n is 2, we have 2 times x to the 2 minus 1, which is 1. That works. When n equals 3, we can have 3 times x to the 3 minus 1, which is 2, and that works. So therefore, what we just showed is that 1 over 1 minus x squared is the derivative, is equal to the derivative of 1 over 1 minus x. Therefore, this value can be rewritten as the sum from n equals 1 to infinity of n times x to the n minus 1. And our original radius of convergence was 1. So my new radius of convergence is also going to be 1. All right, let's look at a very similar problem, but just kind of going the other way. If I want to find a power series representation for ln of 1 plus x and its radius of conversion, what I can recognize is that the integral of 1 over 1 plus x equals ln of 1 plus x. Absolute value. So therefore, I could rewrite this, the integral of 1 over 1 plus x, as the integral of 1 over 1 plus x. Let's do that over here. 1 over 1 plus x we could rewrite as 1 over 1 minus x. So that's a geometric series that has a multiplier of negative x. So that's going to look like 1 minus x plus x squared minus x cubed plus x to the fourth plus dot, 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 dot. And so if I integrated that, I'm going to get x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus dot, 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 dot. And what we realize is we could rewrite this entire thing. So ln of 1 plus x could be written as the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. And there are other ways of writing that sum starting with n equals 1, but this way works pretty well. And what would the radius of convergence be? Well, the radius is going to be the same radius because I integrated this function. The radius of that series is 1. So the integration will result in a radius of convergence of 1. Okay, let's look at how we can combine power series. So let's say we have the following function. We know that we can rewrite that, and we learned how to do this in the last chapter, that we can rewrite that as two separate fractions. And when we do that, we say, okay, well, this is just the sum. The first term is the sum from n equals 0 to infinity of 1 times x to the n. And our other function, which we'll write in red, is the sum from n equals 0 to infinity. Starts with 2, so 2 times, and its multiplier is 2x. So times 2x to the n. And if we look at their respective radii of convergence, this one would have a radius where the absolute value of x, that its multiplier, must be less than 1. So the radius equals 1. And in the next one, to find its radius, we know that 2x must be less than 1. So absolute value of x must be less than a half. So it has a radius of a half. And when we add power series together, the radius of the sum must be the least radius of the two combined. So in other words, here we had a radius of 1, here we had a radius of 1/2. We have to choose the smaller radius because this will only converge for a radius of 1/2. Anything bigger than that, and it will diverge. So we have to choose the smallest radius. So then we could rewrite this whole sum together as the sum from n equals 0 to infinity of 1 times x to the n plus 2 times 2x to the n. And it will have a radius of convergence of 1/2. Or in other words, the absolute value of x must be less than 1/2. All right, let's look at one more function. So let's imagine the power series centered at x equals 0 for the following function, x times e to the minus 2x. Well, let's start with e to the x. We know that e to the x is 1 plus x squared plus x cubed plus all the way on. And then, of course, dividing by the respective factorials. So x to the n over n factorial. So familiarity with all of the major functions, these ones right here, are very important for you to get. So we could rewrite this. Well, let's not actually rewrite it. So therefore, e to the minus 2x, now we're just going to substitute minus 2x every time we see x. That's going to be 1 plus minus 2x plus minus 2x squared over 2 factorial plus minus 2x cubed over 3 factorial. Let's leave it right there. And if we simplify that a little bit, that's just 1 minus 2x plus 4x squared over 2 factorial. And maybe we should write that for us 2 squared. And then minus 2 cubed times x cubed over 3 factorial. The next term, I think you can see that pattern, would be plus 2 to the 4th times x to the 4th over 4 factorial. Okay, and now what if we multiplied by the x? So if we multiplied by the x, if we now are looking at x times e to the minus 2x, we can multiply each of those terms by x. Maybe get x minus 2x squared plus 2 squared times x cubed over 2 factorial minus 2 cubed times x to the 4th over 3 factorial plus 2 to the 4th x to the 5th over 5 factorial. And there's clearly a pattern going on. What is that pattern? Well, we've got 2, 2. So there's always, and maybe it's helpful if I put a 2 to the 1 there. So the powers of the 2's are always 1 less than the powers of the x's, and the powers of the x's are always 1 more than the factorial numbers. So let's see if we can get this right. This would equal the sum from n equals 0 to infinity of negative 1 to the n, and that's to take care of the alternating, times 2 to the n times x to the n plus 1 all over n factorial. And you can do a little bit of testing to see if that is in fact true, and it is. And because e to the x converges for all x, this whole function will converge for all x. And that's it. This is kind of a heavy new topic, but the idea is we're taking these known functions and we're using these 5 functions to be able to write many, many other functions in power series notation.